Okay, in this video I'm going to talk about the second Fermat-Torricelli point of a triangle. Like in the previous video for the first Fermat-Torricelli point, similarly we have an arbitrary triangle, and but now instead of constructing the equilateral triangles on the sides of this triangle outside, like to the outside, so for the first Fermat-Torricelli point we constructed this equilateral triangles like this. So now we construct them to the inside. So instead of this we construct them to the opposite side. So this this and this, right? So these are three equilateral triangles, so let's denote it. So these segments are equal, then these segments are equal, and these segments are equal. So these are three equilateral triangles, and we consider basically the intersection points. So we consider the third vertices of these triangles, and we consider the lines connecting these third vertices with the opposite vertex of the original triangle. So this line, and this line, and the theorem says that these three lines intersect at a single point, and this point is called the second Fermat-Torricelli point of the original triangle. So let's denote the vertices A, B, C, and let's denote this P Q, R, and the theorem says that the lines AP, BQ, and CR intersect at a single point which is called the second Fermat-Torricelli point of the original triangle ABC. Yeah, so let's prove this, and the proof is actually quite similar to the proof for the first Fermat-Torricelli point, but there are still some differences, like it looks, the picture looks different, so it's not fully similar, there are still some differences. So but the general idea is the same. So like for the first Fermat-Torricelli point, the idea is that we consider the intersection points of two of these lines, and we prove that this intersection points also lies on the third line. So let's draw another picture. So we have this triangle, so this is A, BC, this is P, Q and R. So we consider the intersection points of the lines CR and AP. So let's say we take these two lines, it doesn't matter which two, but we consider this intersection. Let's denote it by T. So yeah, so T we denote by definition, right? We define it as the intersection points in intersection point of AP and CR. So yeah, and we need to prove. So now we need to prove that T belongs to the line BQ. If we prove that, then it would immediately imply that the three lines AP, CR, and BQ, they all three intersect at a single point, which is the point T. So yeah, but we don't know yet that. So we need to prove. So that's the main goal now of the proof. We need to prove that T belongs to BQ. So now we consider the. So we recall that these are three equilateral triangles, right? So in particular, like all the angles of these triangles are equal to 60 degrees. So this angle is 60 degrees, and all other angles, like I'm not going to denote all of them, but the point is that, and all the sides are equal. So, but when we yeah, so consider the rotation around. So like we notice that if there is an equilateral triangle, then when we rotate around one of the vertices of this triangle by 60 degrees, let's say counterclockwise, then the second vertex is mapped to the third vertex, right? So like if this is like X, Y, Z, then under this rotation, so Z is mapped to Y. So this is the main property. So we will use this now in this problem. So consider the rotation. So rotation around point B clockwise. Clockwise by 60 degrees. So clockwise, it means like this, in this direction by 60 degrees. So under this rotation, so we notice that BR, the side of the triangle, so ABR is an equilateral triangle, therefore R is mapped to A, right? So the point R is mapped to A, and this is another equilateral triangle, so PBC, right? And when we rotate around B clockwise, then C is mapped to P, right? So we rotate here, so C is mapped to P. So then because of these two mappings, we get that the triangle we get that the triangle RBC is mapped to the triangle ABP, right? Because B, like also the point B stays at the same place. Like when we rotate around B, like the point B itself, it stays in the same place. So therefore, so these are basically the three vertices of this triangle. So these two triangles. So R is mapped to A, B is mapped to B, and C is mapped to P. So RBC. So let me highlight these two triangles. So RBC. This triangle is mapped to this triangle. Yeah, under this rotation. So two blue triangles, and in particular it means that this angle is equal to this angle. Right? So now like as the corresponding angles in these two triangles. So now, because these two angles are equal, so if we consider this segment, so now we consider the quadrilateral ABTR, and in this quadrilateral we have these two equal angles, and this immediately implies that this quadrilateral is cyclic. So so let me write this. So because angles BAT is equal to the angle BRT, as we just proved, as the corresponding angles in these two triangles. So this implies that this quadrilateral is cyclic. Cyclic, it means that it's inscribed in a circle. So like there is a circle that passes through all four vertices of this quadrilateral. So this is one of the criterion of cyclic quadrilateral, that these two angles are equal to each other. So, but because it is cyclic, therefore we have that the other angles. So in particular, so this angle is equal to this angle, but this angle is equal to 60 degrees. So I will just write 60 degrees. So this angle is equal to 60 degrees. Now, and also we have this angle is equal to this angle, but this is also 60 degrees because it's an angle in the equilateral triangle. So ABR is an equilateral triangle, right? So this is angle 60 degrees. So this angle is 60 degrees as well. So okay, so we established that these two angles are 60 degrees, so therefore the third, like the last angle, so this angle is also 60 degrees, either by calculating as 180 minus this 2, or by another criterion of the cyclic quadrilateral. So like this is an external angle at one vertex must be equal to the internal angle at the opposite vertex, and this again 60 degrees. So these triangles are 60 degrees. So now yeah, so let's write here. So the angle, so it implies that the angle ATB is equal to the angle ARB, which is equal to 60 degrees, and the angle ATR is equal to the angle ABR, which is equal to 60. Okay, so let's continue. So so we established that these triangles are equal to 60 degrees. So now observe that the angle, so like this angle is also 60 degrees because it's a angle in the equilateral triangle, right? Like the triangle AQC is equilateral, so this is 60 degrees. And now we notice that the angle, so these two angles, this one and this one, are equal to each other. So they are both 60 degrees, right? So in particular, the angle AQC is equal to 60 degrees and is equal to the angle ATC. Right? So this immediately implies that the quadrilateral AQTC is cyclic, right? Because in this quadrilateral these two angles are like subtending the same side basically, right? So this angle is equal to this angle. So they are both subtending the side AC. So since they are equal, so this quadrilateral is cyclic. This is one of the criterion of the cyclic quadrilaterals, and this implies that the other, so if we now connect Q to T, so like Q to T doesn't necessarily passes through B, so like I deliberately like will draw it not passing through T, so like this, not passing through B. So this line, so QT, so then this angle must be equal to this angle and also equal to 60 degrees. All right, so this implies that the angle ATQ is equal to the angle ACQ and is equal to 60 degrees. So now since so ATQ is 60 degrees, so now we just need to like so you see that ATB is equal to 60 degrees from what we established previously, and ATQ is equal to 60 degrees. So this implies that TB and TQ is the same line. So let me draw this separately. Like, so we have this point T, right? And we established that so here is A. We established that this is 60 degrees. And now there are two segments here. So one is to B and the other is to to Q. Q is somewhere there. So we established that this is an angle equal to 60 degrees. And this is equal to 60 degrees. 60 degrees. And this is equal to 60 degrees. So this angle is equal to this angle. This means that TB and TQ is the same line immediately. So so because the angle ATQ is equal to 60 degrees and is equal to ATB, so ATQ is 60 degrees and ATB is here, is also 60 degrees. So because these two angles are equal, so this implies that that TB and TQ is the same line. So in other words, like, so these 3 points, so T, B, Q are collinear. And another way to put it is that T belongs on the line BQ. So, and this is exactly what we needed to prove. Yeah, so we need to prove that T belongs on BQ. So this is what we proved. So this implies that the lines AP, BQ, and CR intersect at a single point. And this concludes the proof.